Hello all the crazy people out there, my name is Michael, I like wizards and dragons and making games, and let's talk about deferred rendering. So this is the second in a, so far, two-part series about deferred rendering in GameMaker. In the first video, I set up all the necessary geometry buffer stuff. So that's going to be the diffuse color information, the view space normals, and view space depth. And today I'm going to be combining those in the second deferred pass of the deferred rendering system, and this is where we're going to get our final scene containing lighting information and fog and all that fun stuff. So if you haven't seen the first video that I made on this, you're probably going to want to go back and watch the first video that I made on this. All of these cited prerequisites also apply to this one, obviously. But most people don't click on a part 2 video by accident, so I'll assume that if you're here right now, then you're ready to go. So we have our three surfaces with the information about the 3D scene rendered onto them. That's going to be the surface underscore gbuff diffuse, surface gbuff normal, and surf gbuff depth. And these are going to be the three that we need to combine in interesting ways to make something happen in the deferred rendering pass. So I'm going to go create myself a second shader. I'm going to call this SHD underscore deferred. And the vertex shader I can leave alone. My instincts tell me that I'm going to want to get rid of all the stuff in the vertex shader that I'm not using. Partially because I like clean code, and partially because if anybody reads this, I don't want them to be confused about if something is or isn't being used. So the only attributes that are relevant are position and texture coordinate. The only varyings that are relevant are the texture coordinate. I can get rid of all the color stuff. The GL position, I'll leave the object space position alone as it is. And I can get rid of the texture, the vertex color varying rather. And over here in the fragment shader, again, all I need so far, there will be more, is going to be the text chord varying, and we don't need to do any silly multiplying by vertex color, because that doesn't make sense in the deferred rendering pass. I guess if you wanted to tint the screen or something you could, but whatever. So, the first thing I'm going to want to do is I'm going to want to shader set SHD underscore deferred when I actually draw the everything to the screen, and then I can say shader reset at the end. All this down here, these lines of code are just for drawing the little preview surfaces on the side, which are for my benefit and also your benefit, so that you can see what they contain in case you have to debug any of those geometry surfaces. We can ignore those otherwise. I'm also going to want to take these three surfaces and stage them so that we can access them in the shader as samplers. So I'm going to go over to the deferred rendering shader, and I'm going to say uniform sampler 2D, and I'm going to call this samp underscore normal, and uniform sampler 2D samp underscore depth. And the diffuse color sampler is just going to be GM base texture. That's just going to be the surface that we draw to begin with. GM underscore base texture is nothing more or less than a sampler 2D uniform that is automatically supplied to the shader by GameMaker. One of the things that happens behind the scenes when you draw a surface, or when you draw a sprite, or when you draw text or whatever, is that the surface or the sprite or the text or whatever is set as the sampler 2D for GM underscore base texture, and it's just there, nice and easy for you to use in your own shaders, and you don't have to do any fancy setup in order to get them there. So, when it comes to getting the other two surfaces in the shader, the other two texture samplers in the shader, I can say texture set stage, and the sampler ID can be shader get sampler index SHD underscore deferred, and the name is going to be samp underscore normal. And the texture ID is going to be surface get texture self.surf gbuff normal. And the second one is going to be the depth sampler. And I can do very much the same thing here. Give it the correct corresponding name, and we can set the depth sampler. And I do need to draw the diffuse color surface over here when we do this instead of the other one. So right now, that's not going to change anything. We're putting the surfaces on. We're staging the textures to to be accessible in the surface, but we're not doing anything with them. If I run the game now, you can see that all we've got is the diffuse color information, because we are simply taking that from GM base texture and setting it to GL_frag color, and nothing else is happening. I'm going to instead take everything that is sampled from these textures, and I'm going to basically just do a little bit of organization here. And I'm going to say vec4 col diffuse, so the diffuse color is going to be that. Vec4 col_normal is going to be texture 2D, samp_normal. Again, the text chord and vec4 col depth is going to be texture 2D, samp depth v text chord. So we are just going to be sampling the same pixel on all three of these surfaces that we're dealing with, and this is going to give us the diffuse color information in this variable. It is going to be the encoded normal in this variable, and it is going to be the encoded depth in this variable. And if you wanted to set something to a GL_frag color, if you wanted to, for example, put the normal information back on the screen, you could just set the final color to col_normal. If you wanted to do something else with these values, you could do something else. So the first thing that I'd like to do is going to be extracting the normal information. So I'm going to take the normal that was encoded as a color, and I'm going to turn it back into a vector with a range of -1 to +1. And I hope you don't mind if I just copy and paste that function for my example project as well, because once again, if you've gotten this far, you already know how this code works and why it works, and I don't need to, I really don't need to spend airtime going over it again. And I'm going to turn that into a vector, to a normal vector, and I'm going to say fragment normal is going to be equal to get normal from color, and the color is going to be col_normal.red, green, blue. So the red, green, blue components of this color, because alpha is just 1, because we don't need alpha right now. Next, this is going to be a little more complicated, but I can say float fragment depth, and again, this is going to be the linear depth. This is not going to be the scale depth that you would get from doing something like glposition.z divided by glposition.w. This is just going to be linear depth. This is also something that I'm going to copy and paste, although I'm going to give it a little more attention. So the get depth from color function is going to work pretty similarly to the way that it worked in the video I made last year on encoding depth as a color. We're going to take the input color and dot product it against this, I call it the undo value, and that's going to multiply the input vector component-wise against a set of a couple different numbers. That's going to undo the process of encoding it as a color that we did over here. But as was the case in the geometry pass, this color needs to be in a range that is not between 0 and 1, which is what this will spit out. And I'm going to need to, the same way that we divided the depth by the far clipping distance in the geometry pass to get the depth in view space into a value between 0 and 1, to get the linear depth in view space to a value between 0 and 1, we're going to need to multiply this by a similar value, and this is also going to be, I'll call it u_camera z far, and we can set this as a uniform to the shader. Uniform float the far clipping plane, and that is going to give us the linear depth value that is of a value between 0, which is going to be right in front of the camera's face, and whatever the far clipping plane of the camera is. And in the same way as in the geometry pass, when we set that as a uniform, we are going to need to also do that in the deferred pass. We're going to need to assign that as a uniform. And once again, this is very hard-coded. If you were actually making a game, you would most likely not want to hard-code this value. You would want to either set it to a macro if it's never going to change, or set it to a variable if, depending on what your camera needs to do. And this will allow us to say fragment depth is going to be get depth from color col_depth.rgb. And if it helps, If you need to remember that this is a linear depth value and not a scaled one, we can call this get depth from color linear instead. Okay, I probably should do a git commit right here. I'll leave it at that. So this is the depth value of the fragment in the scene. So this is how far away the fragment is from the camera. Getting the view space position from this depth value is a little bit more involved, and there are some differing opinions on the internet as to what the best way to do this is. First, I'm going to not concern myself with the view space depth, and I'm actually going to just not do anything with not do anything that'll involve it, but I'll start with something easy. Let's do fog first, because fog should be the easiest thing to implement. I am going to hard code a few fog values. This is, again, something that should be passed as uniform to the shader from the game, but just to show that it's working first, I'm going to say vec3 fog color can be a vec3. Let's just make it 1 for pure white to make it a little bit obvious. I can say float fog underscore start is going to be 500.0 as my example value, and I'll say float fog underscore end is going to be 3000.0. And we are simply going to do a basic fog calculation, so the fog is going to start attenuating at 500 units from the camera in the world space, and it is going to be fully faded out at 3000. And from here I can say fog, float fog fraction is going to be fragment depth minus fog start, close parentheses divided by fog end minus fog start. And I'm going to want to constrain that between 0 and 1 with the clamp function. And from here we can start concerning ourselves with the final color of the pixel. I'm going to say vec for final color is going to be initialized to color diffuse. Why did I put this down here? I'll put this over here. So the final color can be defined up here before we do anything else. Anyway, final color.rgb can be basically lerped from its default value, so the regular diffuse color value, so whatever it already is. And this can be lerped to the fog color based on the fog fraction. And that's going to get us some basic depth. For those unaware, linear interpolation, the lerp function, for whatever reason, the authors of the OpenGL shader language chose to call it mix instead. I guess like it technically makes sense why it would be called mix, but also everyone else calls it lerp, so why didn't they? I don't know. Anyway, let's run this. This is going to give us some basic fog, things in the distance, and we're still rendering the normal color instead of the final color. Let's change that. Things in the distance will be fading out to white. So you can see the mountains in the distance are fading out to white. We've already got a bit of a sense of depth in our 3D scene. If I keep walking this way, we are going to have more and more of the mountains being fogged over, and they are indeed slowly fading out. Fog is behaving as intended. If I were to look at the trees in the distance, we can see that the trees are also starting to fade as well. All right, great, that's fog. Let us do another commit there. It's not a big commit, it's only a couple lines of code, but it feels like we accomplished something, so I think that's worth celebrating. Next, we can also do something with something a little more complicated with perhaps a light source. I am, again, going to hard code some stuff. Let us hard code vec3 light color is going to be, let's I'll mark off the sections where I'm messing around with a comment like this. Hopefully that makes it easier to follow. We can hard code the light color to be vec3 111. Basically the same color as the fog, so the light is going to be white. Let's also say the vec3 light direction is going to be, I like to use a vector 3 that's something in the realm of like, 1, 1, and -1 for testing lights. This is going to be a matter that's a little bit complicated. I'll show how this is going to differ a little bit from forward rendering lights in due time. But remember that our normal that we encoded is in view space, and the depth that we have extracted from the depth texture here is also in view space. And for all the lighting calculations, we're going to be working in view space here instead of in world space. So we're going to want to treat these lighting vectors and positions and such a little bit differently than we would in forward rendering. But for now, float n.l is going to be the classic dot product of the fragment normal against the light direction. And this should be the negative light direction because math reasons. If you want the surface to be fully illuminated, if the normal of the surface is going in the opposite direction of the light ray, might be a tiny bit more efficient to put that negative in front of the dot product like this, but overall, it's the same. And then, lastly, this shouldn't be less than 1, because if it's less than 1, you don't want n.l to be negative. So we can say max of 0 and that value, and that will constrain the n.l value at 0 if the light isn't shining on the triangle at all, on the fragment at all. And a basic lighting function might be to simply multiply the final color.rgb by, so final color.rbg times equals n.l multiplied by the light color. And this is going to give us some lighting. It is perhaps not going to give us the lighting that you expect. And for one, we are kind of sort of lighting the bottoms of surfaces, which isn't really what you want. With the z, the positive z up vector that we're using in the rest of the game, it might be more expected that if a light vector is coming down in this direction, then it should be shining down on the scene. But that is not the case, because remember, in view space, positive x is going out the right side of the screen. I'm gesturing in midair, as if you can see me. Positive y is going up through the top of the screen, and positive z is going out into the screen, so that is the distance away from the camera. And any lighting vectors that you deal with in the deferred rendering shader here, the way that I've got it set up with everything in view space, you're going to want to transform those lighting vectors also into view space. And this is where passing these values in as uniforms would really be easy, because you can simply take a world space vector like this, multiply it by the camera's view matrix, and then you get the vector in view space for free. You could also do that multiplication in the fragment shader. It is not ideal to do matrix multiplications like that in the fragment shader when you could also just do it in GML and pass it in as a uniform. And I will talk more about that when we get to figuring out the view space position from fragment depth. But for now, let us set up a couple more uniforms. We can call this uniform vec3 u underscore light direction. I'll keep the light color hard-coded for now, because I don't want to spend any more time than I have to messing with that. And we can take the light direction vector, feed that into the m.l instead of the hard-coded one over here, and I can also pass in the light direction value. I do not trust myself to spell that correctly, as a uniform over here. So if you were to simply pass in the values of 1, 1, -1 over here, this wouldn't really be any different than what we were doing before. We are going to instead need to transform this into view space. And again, GameMaker gives us a handy matrix multiply function, or a matrix transform vertex function that you can use. And I am not currently saving this this view matrix to a variable. I should be doing that. That's a constant, isn't it? I'm going to call it mat view is going to be equal to that. Self.mat view is going to be set to the view matrix. You could do the same with the projection matrix, but we don't need the projection matrix for anything here, because we're not dealing with anything in screen space or in normalized device space or anything like that. Anyway, going back to post draw, if my original lighting vector, I'm gonna call it light. How do I want to do this? I'll just make that a little GameMaker struct. So we have our light direction. If we want to transform that into view space, we have matrix transform vertex. And the matrix that we can multiply by is going to be self.mat_view. And the x, y, z, and this is actually fairly new. GameMaker allows us to pass in the w coordinate into the matrix transform vertex function. If you want to do something like multiply a vector by a matrix instead of a position. But the position is going to be light direction dot x, light direction dot y, light direction dot z, and the w coordinate is going to be 1. This is going to be just like multiplying a vector, a normal vector, by a matrix in the vertex shader. So when you multiply a vector by a matrix, if you want the vector to just represent a direction and not a position in space, you want to give it a homogeneous coordinate of 0, and that is going to prevent it from being like transformed in space in any weird ways, and it's simply going to basically rotate and scale it. We're doing the same thing over here. So we are multiplying the view matrix by a vector 4 comprised of the light direction x, y, z, and a homogeneous coordinate of 0. And this is going to return an array of 3 values. I'll call that transformed light direction. This will not necessarily have a magnitude of 1. This will not necessarily be normalized, so I would like to this is far too long of a variable name. I will simply get the magnitude of this vector and then normalize it myself. GameMaker, unfortunately, does not have a built-in vector normalize function. And now we can set. Come on. We can set these 3 values as the 3D vector for the light direction in the shader over here. And the light vector will be transformed into view space, and we can proceed. And if I run the game now, the game should be lit as if it has a light source coming down from that direction. All right. It is actually not perfect. It's better, but I feel like I made a typo. Did I? Okay, you know what? The normals on the trees are fine, but something tells me that the normals on the mountains are actually not fine, and that is probably because this would be a really dumb thing to get wrong if I did. The view space normals are not being normalized, are they? Which they should be after scaling. And boy, I will have shown a. Yeah, that looks a lot better. Okay, I commented out the fog just to make it a little easier to see what's going on those mountains. I will have thrown text on the screen in the first video, reminding myself to do that, because I forgot to do that, because that is something that you do have to do after transforming a normal by a matrix with, which potentially can have scale, because if your normal vector does not have a unit length of 1, then you're asking for trouble. Anyway, this is a directional light. Everything looks good. We have the lighting correct on those mountains in the background. You can sort of see the angle that the light is coming down from. I don't offhand know like exactly where my bearings are in this 3D scene, because I don't know which direction is like up, down, left, right, or whatever, north, south, east, or west. But you can see that it's approximately going in this direction. This side of all the trees are lit. The back sides are not. We have a directional light. And we have successfully transformed our directional light from world space into view space by multiplying it by the view matrix. Okay. Let's see. I think this is a good time for another git commit. What did we do? We've got ourselves a directional light in the deferred pass. So next, let us go and deal with point lights. So the things that we've gotten done in this video have gotten progressively more complex as we've gone along. Pixel fog, at least this implementation of pixel fog, only really cares about the distance of a fragment to the camera, which we can get simply enough. Directional lights only really care about the face normal of a fragment of whatever you're trying to draw, and we can get that nice and easily. Although we have to transform the light direction into view space, which is a little bit more. And the matter of point lights. Point lights are going to need not only the normal direction of whatever we're drawing, the normal vector, but we're also going to actually need the position in space. And this is going to get a little bit involved when it comes to figuring out our position in space. There's a couple ways to do this. A common one that you'll see is to take the fragment depth and basically go backwards through the transformation pipeline from normalized device coordinates to, well, first from like screen space, from texture coordinates, using the v_v text coord value, and that will be our texture coordinate, and then you put that into normalized device coordinates, and then you multiply that by the inverse view matrix to put it in view space, or the inverse projection matrix rather, to put it in view space. But that's a lot of work, and multiplying things again by matrices in the fragment shader is not the best way to do things a lot of the times if you have alternatives. I'm not going to get into what exactly the 16 values in a projection matrix are, and what happens when you matrix multiply that by them, because, and let's be honest, these videos already go on for long enough, and you all really don't want to sit here for 10 minutes listening to me saying math words. But the essential part of the shortcut that I'm going to do to turn the depth value into a position in view space is that a lot of the multiplication values that you do, a lot of the multiplications that you do when you multiply something by a projection matrix or the inverse projection matrix actually cancel out to 0, and they're kind of redundant and don't really need to be done, and you can actually extract a lot of the work that would come from multiplying by an inverse projection matrix. And what you're left with is just going to be a few lines of code and a few vector multiplies, and we don't need to deal with inverting the projection matrix, or God forbid, if you wanted to work in world space for everything in the fragment shader, you'd also have to invert the view matrix and multiply the view space position by that. And that's not something that anybody really wants to do. When I said working in view space would make our lives quite a bit easier in the first video, that's the main thing that I was referring to. So, I am going to write myself a function. I'm going to call it vec3 get position from depth. This is going to take an input float. This is going to be a depth value, and this is going to return a vector 3, which is going to represent our position in world space. So if you were to multiply, basically it's going to be this. What we're going to end up is going to be this, plus or minus some floating point imprecision, but it's going to be a small amount of floating point imprecision, and it shouldn't really affect our scene in any major way. So the first thing that we need is to take the screen space coordinates, which is going to be v_v text coord. So that's going to be a value between 0 and 1, representing the pixel on the surface that we're drawing, and we'd like to transform that into, we're going to give it a similar transformation to getting normal from color and encoding normal as a color. So we want this to be a normalized device coordinate position, and I suppose coordinate position is redundant, isn't it? But we're going to want to transform our texture coordinate into normalized device space, which is going to be a vector with a range between -1 and +1, with basically 0, 0 being the middle of the screen, 1, 0 being the right side of the screen, like that. And that's going to be a vec2 because we only care about the x and y here. And we can get this, I'm going to call it vec2 ndc for normalized device coordinate underscore position, and that's going to equal 2.0 multiplied by 0.5 minus v_v text coord. Instead of subtracting 0.5 from the texture coordinate, we're doing it the other way around, because in screen space, we want the positive direction to be down on the screen, but in a normalized device space, we want positive to be up on the screen. So we're going to have to invert this by switching the order of these two operands over here. And the view space position is going to be the result of a fairly interesting calculation. This is going to be the main part of what I mentioned a minute ago about doing some cheating with the projection matrix. I'm going to say view space position is going to be simply a vector 3 comprised of the normalized device coordinate multiplied by depth multiplied by And we're going to have to think a little bit about the field of view and aspect ratio of the camera, of the 3D camera, of the projection camera over here. 60 degrees and 16:9 aspect ratio is what those are right here. And we're going to need to feed those into the shader with a uniform as well. But I'm going to finish typing this out first. I'm going to call this U underscore FOV scale. So that's going to be the field of view scale. And that's it. So that's going to be the value on the X and the Y, because the NDC position is a vec2, a 2D vector. And vec3 wants a third value. And this is simply going to be depth. And once we're done with that, we can return view space position. You could return this value directly, but I'd rather give it a name, just to make sure everybody knows what this does. So this is going to be getting the 3D position in view space from depth. I first need to define this as a uniform. So uniform vec2 U underscore field of view scale. And this isn't going to do anything interesting until I actually set those uniforms in the post draw event over here. But lastly, and this is going to be the third and final one of the positions I'm going to reconstruct, the values I'm going to reconstruct. Fragment position is going to be get position from depth, col underscore, actually this is going to be fragment depth, because that's all you need. You don't need the original depth value or anything like that. And this is going to be our fragment position in view space again. I suppose for the sake of clarity, I'll add VS to the end of this also, just to make sure that everybody knows what coordinate space we're living in here. You could say fragment position. Nah, I won't append VS to that as well. So let's come over here and let us figure out exactly what we need to do with respect to the field of view scale position. So once again, this is going to come from the transformations that you would do when you multiply something by the projection matrix, and when you build the projection matrix is where this would happen originally. If anybody's curious, this is what the values inside a projection matrix look like. We cannot simply pass in, for example, -60 for GameMaker reasons is my field of view, and -16/9 for GameMaker reasons is my aspect ratio. We can't simply pass in these two original values as they appeared in the projection matrix over here. We're actually going to need to do a little bit of math on them. And FOV scale is the name. We are not putting that in the light direction vector. The field of view, when you set up a projection matrix in GameMaker, you might notice is labeled field of view underscore Y in the code help. And this is indeed going to be the vertical field of view. You can think of field of view and aspect ratio in a 3D camera, not only in terms of the vertical field of view and the aspect ratio, but you can think of them in terms of a horizontal field of view and a vertical field of view. And I suppose in a lot of ways it's more helpful to do field of view and aspect ratio, but when it comes to actually building the projection matrix, what you really want is the horizontal and vertical field of view. And let me set those as variables. The horizontal field of view is simply going to be the vertical field of view. I guess I can call that field of view Y as well. Multiplied by the aspect ratio. And obviously, the vertical field of view value is simply going to be that as it is. It's just going to be the vertical field of view. Don't need to transform it. So next we want to divide both of these by 2, because we really want the basically half the field of view. So this would be the viewing angle that you can see on like half of the screen. Horizontally or vertically, so we're going to want to divide both of these by 2, and then we are going to want to transform, we're going to want to take the tangent of these values. That is not how you spell tan. That is how you spell tan. And because these values are in degrees and the raw trig functions like to take radians as their inputs, we are going to need the degree tan, the degree version of the tangent value. And this is our final field of view scale value that we are going to pass to the fragment shader. And multiply by the normalized device coordinate position and multiply by the depth to give us the view space position. So it's not the easiest to test if this is going correctly, if this has gone correctly. Shaders don't really have a great way of being debugged. There are tools such as RenderDoc that you can kind of plug into GameMaker and sort of peek behind the scenes at what's going on in the rendering of a game, but it's not the easiest. You might want to just straight up output something like the fragment position, the view space position to the screen by assigning GL frag color equal to, instead of an actual color value, something like fragment position. Transforming our depth into a view space position is more or less working. Although, again, I suspect that our aspect ratio and field of view being negative are gonna cause some problems, which I don't really want. It's another GameMaker thing. You don't really have to worry about that if you're not trying to draw sprites directly, but I will save that rant for a later time. So let us set up a point light. How long have I been recording for? Because this is like, I've been recording for almost an hour and I haven't even gotten to point lights. Anyway, let's hard code some stuff again just to get it set up. We can do this very much the same as before. Vec3 point light color can be Vec3 1, so that's just going to be a white light. If you want, you can mess around with these and make them other colors, but white will suffice for my purposes. Vec3 point light position can be, let's make this, if I want it to be, let's say over the player's head off the ground, 160 units off the ground, so Vec3 0, 0 on the XY and 160 on the Z. And I can say hardcode float point light range to, let's say, 400 units. And if you're thinking in terms of view space, you can already see where this is going to go wrong, but let's have some fun by running this code incorrectly first. I guess I'll define Vec3L in this case is going to be the point light position minus fragment position. This is going to be a vector. This is going to be the lighting vector, so we want this to be normalized. I can say float dist is going to be equal to the distance between the point light position and the fragment position, because again, point lights do care about where you are in space relative to the light source. N.L can be the dot product of the fragment normal against the light vector, and this doesn't have to be negated the same way that the directional light did, because the order of the subtraction operands here in the subtraction over here. And as always, we want to max this of 0.0 and 1 so that it will never be below 0, so it'll be clamped down at 0. And then there is the matter of the light attenuation, which does look a lot like the fog attenuation in some ways. Float attenuation is going to be equal to the light point light range minus the distance divided by the point light range. That is going to want to be clamped, actually min of 1.0. Actually, hang on. Yes, clamp. I was right the first time. Clamp between that and between 0 and 1, so that it will, the attenuation will never be less than 0 or greater than 1. It shouldn't ever be greater than 1 anyway, because that would imply that you are negative distance from the light, which doesn't make sense. But let's see. I will disable the directional light so that everything we see on screen will be influenced by the point light. And here I can say final color.rgb multiplied by equals n.l multiplied by the point light color multiplied by the attenuation. Again, very basic point light code, but we should have at least something, even if it does not exactly behave the way that we want. And clamp is complaining because I have a parentheses in the wrong place. Understandable. So, if you think about view space position, 0, 0, 160 is going to be 160 units away from the camera, in front of the camera. And if you look at the way that the light is going to behave on the ground as I move the camera, that's pretty much what's happening. You can think about like a ball of light hovering some distance in front of me, basically where the mouse cursor is. And if I move around, the light's influence is being correctly calculated on the things in the scene. If you wanted to have a ball of light some distance away from me, in front of me, where the mouse cursor is. And you can't really see it very well if I do this, but if I tilt up a little bit like this, you can see that the spot of light gets a little bigger on the ground. If I tilt down, it gets much more concentrated at a point, as if it's the ball is hovering just a few inches above the ground. And just the same way that we had to transform the directional light vector into view space before doing anything with it in the shader, we are also going to have to transform the position of the point light into view space. And that's pretty much going to look the same as transforming the directional light did. If I just create myself another uniform, I can call this uniform vectory light point position. And we can use this as the point light's position over here instead of hard coding this value. And if I go into post draw, I can do something very similar over here. We can, instead of saying light direction, we can say light point like this. We are going to want, since this is a position in space and not a vector, we are going to want to give matrix transform vertex a homogeneous coordinate of 1. Again, when you transform positions in space by matrices, you're going to want to use a homogeneous coordinate of 1 instead of 0. Everything else does not have to be normalized. I do not have to do any of that. We do not actually want the position of the point light in space to be normalized, because that would kind of be pretty useless. And then the light point value, and I've already forgotten what I have named the uniform. The light's point value in view space is simply going to be the result of this transformation, and we can supply these three values to the shader. And now if I run the game, we should have our 3D scene, and the point light is illuminating things from the bottom. Okay. That is actually not what I wanted. Oh, that's because I am still using... Yeah. An overwhelming majority of the time, when my code doesn't work in these videos, it's because I did something silly like that instead of because something's actually broken. Sometimes it'll be because something is actually broken, but usually it's because of something silly like this. Alright, so now when I run the game, we should have a point light hovering some distance above the player's head. And when I walk around, you can see that, and I'm zooming the camera all the way out. Unfortunately, you're not lighting up the player. Oh, you know what? It's not above the player's head. It's the fact that the aspect ratio needs to be negative if I have a negative aspect ratio here, but not the field of view. It's the continued bane of my existence. If you're not using negative field of view and aspect ratio to get around GameMaker problems, then this won't be a problem for you. But unfortunately, since at least the DNA of this project has me having to do that to get around GameMaker problems with like drawing sprites and stuff and tile maps and stuff. Yeah. Anyway. We have a point light. It is centered around basically this tree in the middle. It looks very special, I know. That is doing point lights in deferred rendering. I will not be covering spotlights because this video has been going on for a very long time and I would like to give my throat a rest. But if you know how spotlights work, you should be able to transform the spotlight's position and direction into view space, and you should be able to plug in the corresponding values into from the spotlight calculations from fragment normal and fragment position and all that, and you should be able to do it. There are other things you can do in deferred rendering. I don't immediately have any plans to cover them. I just wanted to cover the important parts, which are basically this. That is going to do it for me for today. I hope you all enjoyed this. Deferred rendering is a very interesting subject. It's definitely not something that all games need, even perhaps most games in GameMaker need, but knowing how to do it, I think, will give you a bit of a new perspective on how rendering works. If you want the code for this, look for the GitHub repository down in the video description. I try to post a couple of game dev videos a week, so if you're interested in any of the weirder things you can do in GameMaker, feel free to subscribe. I have a Patreon, so if you want to contribute to the channel, links to that can be found in all the usual places. Otherwise, I hope you all found this useful, and I will see you all later. Special thanks to Army Armbuster, DJ Gibbles, Edward Holt, GameMaker, Harold Guidry, Jonathan Bernardez, Kiexi, Sindra Larson, Squarecrowd, The Oz, and Zenjamin for supporting these videos. If you want to support the channel, head on over to the Patreon page down in the video description to join the fun.